Welcome to the overview talk on WRF physics. This one covers radiation. The radiation has these two switches, long wave and short wave. All the physics interact with each other, including radiation and microphysics, which interact through cloud effects, and radiation and surface, which interact through the direct radiation to the surface. In the model, the radiation provides the atmospheric temperature tendency profile and also the surface radiative fluxes. So there are many processes in radiation that we have to account for. One is the diurnal cycle, of course, and the seasonal cycles, but also the sun interacts with the clouds through the albedo effect of clouds and also absorption, interacts with clear sky through absorption and scattering from particles, and the long wave interacts directly with clouds too, which have a strong blocking effect on long wave radiation, infrared, and also the long wave and the surface interact, as do the shortwave and surface. So the long wave scheme has to compute the clear sky and cloud upward and downward radiation fluxes. And so we consider IR emission from layers, and the surface emissivity is based on the land type. The flux divergence of the emission from layers leads to cooling in a layer. The downward flux of the surface is important in the land energy budget. It's a few hundred watts per square meter. Infrared radiation generally leads to cooling in clear air of the order of 2 degrees per day, and there's stronger cooling at cloud top and warming at cloud base. WRF has several options for long wave radiation scheme. I'll not go into all of them in detail. RTMG is the most favored one currently. It is also used at the European Centre and in climate models and in NCEP operational models. This summarizes the radiation schemes in terms of how they interact with the microphysics and what kind of cloud fractions they have, as well as how they deal with greenhouse gases. They have a variety of methods, and I'll go into those in more detail later. In clear sky, there are three main gases that are infrared active. They are water vapor, which comes from the model, of course. CO2 is a well-mixed gas. You can specify a constant for the whole atmosphere. We have a couple of ways of doing that now. In the most recent version, CO2 can also be calculated from the year. In the other interactive gas, of course, is ozone, which also has its own climatologies. CAM and RTMG have a monthly zonal and pressure level climatology. Others, like Goddard, use a single profile. This diagram summarizes the shortwave and longwave spectrum of the radiation. On the shortwave side, you can see which gases have most effect, and that's mainly the water vapor, very little effect of carbon dioxide. On the longwave side, again, a lot of water vapor effect, but also some from carbon dioxide. And then we also see the effect of ozone in the shortwave at the ultraviolet end. And then there's methane, which has a couple of effects in the long wave especially, nitrous oxide. Ozone also has a slight long wave effect. But the main long wave effects are from water vapor and carbon dioxide. The shortwave and long wave spectrum are divided into two parts, really, for the model. The shortwave is incoming from the sun and has this spectrum with a peak less than 1 micron. The long wave spectrum peak is around 10 microns and is basically the long wave emitted from the Earth. So the schemes divide the spectrum into bands. Typically for RTMG there are 16 bands. The computations in these bands use lookup tables that are generated by more accurate line-by-line radiation models. In radiative transfer, there are upward and downward beams. It's known as a two-stream approximation. So on the left we have the upward beam, and on the right we have the downward beam. And for each model layer, we're computing the flux at the top and bottom of the layer. And it's basically an upward and downward integration. The temperature tendency is the flux divergence given by this formula at the bottom, where the rate of change of temperature in a layer depends on the flux divergence across that layer. So the flux is diverging, that's a cooling effect. As mentioned, to compute the radiative transfer, we need the flux in each layer. So the flux is given by an integral of B, which is a function of temperature and frequency, over d epsilon, which is the emissivity. This is turned into physical space integration in the model. So for B is the Planck function of the frequency, and for FDN here, you do an integration upwards from each level. So this is integrating the emissivity of the layers n and n plus 1 all the way up to the top, and to give you a final value of f at the level n. Then this is basically a summation of the B contributions from each layer above. And the emissivity of each layer depends on the gases, the clouds, the aerosols, pressure and temperature in the layers. And again, lookup tables are used to compute those numbers to fill in that integration. After you've done that, you get a downward flux and an upward flux seen in the bottom diagram here. This is the ground and the top. The upward flux is a maximum near the ground and decreases upwards. The downward flux is 0 at the top and increases downwards. This is basically emission from the atmosphere. The upward flux is emission from the surface, but being depleted by the cooler atmosphere as you go up. The net of these two is a flux that decreases as you go down. And as you see, the upward flux is converging with height, which means there's a warming, generally a warming from the ground into the atmosphere. The downward flux is diverging as you go down. So this is a cooling, which is basically the atmosphere radiating to space. The net is also a diverging, which is basically a cooling. So the long wave net effect is a cooling one. Clouds are obviously important for long wave radiation. All the schemes interact with the resolved clouds that the model predicts from the microphysics. Some microphysics options also pass the particle sizes to the RTMG radiation option. Those particles are the cloud droplets, the ice crystals, and the snow. Those have the largest radiative effect. Other combinations of microphysics and radiation only use the mass information from the microphysics, because the radiation is able to compute or make an estimation of the particle sizes for itself when they're not provided. Rain and Graupel are much larger particles and per unit mass have very little radiative effect, so most schemes tend to ignore the radiative contribution of Rain and Graupel. Clouds strongly affect infrared radiation at all wavelengths, so they're considered grey bodies. They don't really have a spectrum, and they're almost opaque to infrared radiation. Radiation schemes can also handle cloud fractions, where only part of the grid cell is occupied by clouds and the rest is considered clear. So we have several ways of doing cloud fraction in WRF. One is the Shue-Randall method, which is only less than 1 for small cloud amounts, but is 0 for when there's no resolved clouds. Cloud 2 is the simplest option, which is either 1 or 0 based on whether there's a small amount of cloud in the grid cell or not. So that doesn't have a fraction. Cloud 3 is a Thompson option, which can have clouds, a cloud fraction even when there are no resolved clouds. It's based on the relative humidity. So the fraction is between 1 and 0 and can be non-zero when there's no resolved clouds. It's the only option that does that. The Cloud fraction can also be provided by convective clouds, and the CURAD feedback option is a switch. You can turn on or off the effect of convective clouds on the cloud fraction. There are only a few convective schemes listed here that actually provide that cloud fraction. Given a cloud fraction at each layer, because that's a three-dimensional field, you have to make an assumption about how the clouds overlap. There are several different ways of doing that. One is you can assume each layer randomly overlaps with all the other layers. That's not very realistic. Another is maximum overlap, where the layers are stacked as much as possible. That is a bit more realistic, but the one that's often used is the maximum random overlap, which is a combination, where neighboring cloudy layers are maximum overlapped, but when there's a clear sky between the layers, those are randomly overlapped because there's no reason to believe the clouds at two different layers should be maximum overlapped. So the maximum random overlap is the option most used by radiation schemes. RTMG and CAM are popular schemes that both use that option. RTMG also has a new overlap option which allows an exponential variation on the overlap assumption called cloud overlap. So you can modify the RTMG one with this new option if you want. Now we come to the shortwave radiation options in WRF, which are given by this switch, RASW physics. This has a lot in common with the long-wave schemes in terms of what it has to deal with, but there are some important differences. So in the shortwave, we're computing the clear sky and cloudy solar fluxes. It includes annual and diurnal solar cycles, of course, and most schemes will consider the downward and upward reflected fluxes. The simple scheme that I have was only a downward flux. Basically, anything reflected is lost immediately. Primarily, it's a warming effect in clear sky, and it's an important component of the surface energy balance. This slide summarizes the schemes we have in WRF. Again, RTMG, the shortwave option, is probably the more popular one, but we also have a new Goddard scheme, which is in some ways faster. And there's RTMG-K, which is a Korean version of RTMG that adds some efficiency. But this summarizes the schemes. And in this slide we have the overview of how they interact with the microphysics and the chemistry. You'd note that the ones with chem-tau are interacting directly with WRF-Chem, so that's the old Goddard, option 2, and the RTMG that interact with WRF-Chem through this optical depth, which is what chem-tau represents. And that's usually aerosols. And then the microphysics interactions are here as well. The schemes interact with the microphysical particles the same way as the long wave does. Cloud fraction again, same as long wave. The ozone is more important for shortwave, and some of these schemes have a more sophisticated treatment of climatology than others. The ones with latitude and month have a climatology that is basically latitude, height, and month. And the RTMG has that as an option. Actually, that's the default now in RTMG, but it came from the CAM radiation scheme originally. So in clear sky, aerosols can be important for shortwave radiation. So if you're not running chemistry, we do have other options of how to handle aerosols. So again, the main gas effect in the clear sky is the water vapor, but there's also a CO2 effect in the shortwave spectrum. Aerosols would be needed for additional scattering. WRF-Chem interacts with both Goddard and RTMG shortwave. My scheme has a tunable scattering parameter. It's just a single number you tune. RTMG has other climatological aerosol options too. AEROP1 is a European Centre climatology called the Tegan climatology. It's a global monthly climatology of aerosols based on, I think, 6 different types. AEROP2 is where a user can specify their aerosol optical depth from a map, which may come from satellite, for example, or some analysis. But it's basically a 2-dimensional aerosol optical depth map that gets scaled with height. and interacts with both the Goddard and the RTMG radiation schemes. AROP 3 is a special one that goes with the Thomson microphysics and interacts with the aerosols that come along with their aerosol version of the Thomson microphysics scheme. So you would advect those aerosols in the model as well. And AROP 3 is a special type of aerosol that scheme has, the water-friendly and ice-friendly aerosols that are also now interacting with the radiation option. As mentioned, the ozone is quite important for the shortwave, especially in the stratosphere, because it maintains a warm stratosphere. So any long simulations, including the stratosphere, need to include radiation that interacts with the ozone and a reasonable ozone climatology. So it's important for model tops above about 20 kilometers or 50 hectopascals. We usually specify it from a profile. It was the same ozone as in the long wave option. But as I mentioned, the CAM and RTMG have this zonal climatology that's also monthly, so it's the best way to deal with the ozone and the stratosphere. Also, there's trace gases that these schemes can handle as well. They're usually just set constant. As with the long wave, the shortwave scheme has spectral bands, which are handling different parts of the spectrum separately. Here we have RTMG bands 16 to 29. 16 actually overlaps with the long wave spectrum. And the bands are dominated by different gases typically, as with the long wave. And the calculation is done with lookup tables. So a lot of similarity, it's just the bands are different and the calculations for those bands are different. Radiative transfer, I won't go through that again. It's very similar to the long wave, except in some ways simpler. In contrast to long wave, shortwave has no emission from the atmosphere. So in that way it's simpler, but it does have reflection from internal layers. So you have to treat both an upward and a downward beam at every point, at every level, which complicates the integration. It's not just a simple upward and downward integration that the long wave has. There's a matrix solution you have to solve to allow for this reflection from layers, which is important to treat. The only exception is the simple scheme that I have, which only does a downward integral and neglects any further interaction of the reflected beam. As with the long wave, the cloud fraction is also important, and the clouds, they're very similar the way you treat long wave and shortwave clouds, but the clouds in the shortwave do have an important reflection capability, of course, with the cloud albedo, so that has to be included, as well as these diffraction and the overlap assumptions. There's also surface albedo reflection, which is based on a land surface type and snow cover. An additional feature of shortwave radiation that we have in WRF is the effect of slopes. So this only affects the shortwave impact on the surface. For example, a south-facing slope during the daytime in the northern hemisphere will have more radiation than a flat surface. So this accounts for the slope, the resolved slopes in the model, and how they impact the shortwave impacting the surface. So it accounts for the direct sunlight fraction, because you only get this effect for direct sunlight, and the slope aspect relative to the solar position. There's two levels of detail. The first one is slope rad, which activates the slope effects, and is the direct change of radiation relative to the solar angle and the slope aspect. The second level of detail, which is probably for much higher resolution, is topo shading, where actually neighboring grid cells can be shaded by mountains. So the slope rad could be used for grid sizes less than about 2 kilometers, where you're resolving the slopes. When you're 3 or 5 kilometers or 10, you probably don't need this, because the slopes in the model are very averaged and not really representing the local topography. So I would recommend not using this effect until you're below about 2 kilometers and resolving the individual slopes. The topo shading also, you probably want a less than 1 kilometer, because that's where the shadow of a mountain may extend more than one grid cell. And it's a much more complicated piece to do numerically because of the non-local effect. All of our radiation calculations, apart from this, are a vertical column, independent columns. but this Topo Shading actually adds a horizontal effect as well, which makes it a lot more complicated. So I'd only use that at very high resolution if you're interested in that effect. So radiation is part of the physics that actually is very expensive to run. So we don't run it every time step. We instead have a time step that we designate for radiation called RADT in minutes that you would specify. Typically then the radiation runs about every 10 time steps. Our rule of thumb for this is 1 minute per kilometer grid size. The main reason for this frequency is it should resolve the cloud cover changes with time. And so as the clouds move, you want the radiation to keep up with them. So having 1 minute per kilometer grid size is roughly going to keep up with the clouds. That's the main change that occurs at high frequency. Each domain can have its own value, but we would probably recommend just using the same value on all 2A nests. This rule combined with the model time step rule, as I said, is about one radiation call every 10 time steps. Surface shortwave fluxes. We do have a swintopt equals 1, which is a shortwave interpolation option. That allows a smooth variation of downward solar flux during the daytime because we can scale for the changing solar zenith angle, the cosine of the zenith angle. So when we scale each time step, we use a new cosine zenith angle, and that gives you a shortwave radiation that changes gradually as opposed to stepwise with the radiation step. This allows smoother forcing of the surface variables. So things like the skin temperature, you'll see the steps disappearing when you turn this option on. If you're looking at time series of every time step, you'll see this effect. Generally, the effect is very small if you're not looking at that. So it's really mainly to help you with your time series plots and making them look nicer is to have this option. We also have diffuse direct and direct normal components output, which are of interest for solar energy applications. So we have these extra output names that you see listed here. Aerosols mostly affect the diffuse direct ratio, but not really the sum of them so much. So aerosols, you'll see the impact more in the direct radiation, reducing that, but it won't affect the surface downward flux total, which is the direct plus diffuse. So that ends the radiation talk. As I've mentioned, the radiation interacts like in this diagram with both the clouds in the model through the cloud effects and cloud fraction, and also directly impacts the surface through the downward shortwave and longwave fluxes. The surface also has some impacts on the radiation through its emission and the albedo, which impact how much upward flux there is, both in the longwave and the shortwave.